Hello everyone. Today we will discuss a few more properties of expectation and variance. Okay, in the multivariate scenario. So basically, expectation of vector, expectation of matrix, and then variance of vector. We won't go for variance of a matrix. So we have defined expectation of a vector and we have defined expectation of a matrix. They have also defined variance of a vector, and we discussed how the variance covariance matrix would look like. So we said that variance covariance matrix is going to be symmetric, correct? That is one property that we discussed. The matrix would be symmetric because covariance is symmetric. Second property that we discussed was diagonal entries would be always non-negative. Okay, diagonal entries would be greater than or equal to 0. And there is third important property which I did not discuss yesterday because I wanted to go slightly into more details. Every variance covariance matrix is non-negative definite. Okay, it is non-negative definite. Do you remember linear algebra? What is the definition of non-negative definiteness? Can anyone tell me?
Yes, ma'am. Suppose we have a vector x, then x curl transpose A into x curl will be greater than equals to 0.
Okay, for which x? For which x would x prime ax be greater than or equal to 0? Is my question clear?
Yes, ma'am.
Yes. Others? You are also welcome to answer.
Madam, since this is a symmetric matrix, you can see the eigenvalues are non-negative.
Sorry. Can you repeat?
Since this matrix is a symmetric matrix, so the non-negative definite matrix for symmetric is that the eigenvalues are non-negative.
Okay, yeah, correct. So one definition of non-negative definiteness for a symmetric matrix is the eigenvalues are eigenvalues are also non-negative. Correct. Anything else? I want answer to that x thing. For which x is x prime ax greater than or equal to 0?
A random vector x1 expression.
Random? It's mathematics. Why do you need randomness? In linear algebra, why do you need randomness? Can you make it more precise?
Ma'am, it must be for all x. If A is positive semi-definite or non-negative definite, then x transpose A x will be greater than equals to 0.
Correct. For every vector x which is of the given order, so if your A matrix is P cross P, let's say, then for every x which is of order P cross 1, x prime ax would be greater than or equal to 0. Correct?
Also, ma'am, the diagonal elements of A must be non-negative in that case.
Diagonal elements must be non-negative. Okay. Any other property? So we have already studied two definitions. One is x prime ax should be greater than or equal to 0 for every x. Second is what Pushkar told. If you have a symmetric matrix, then every eigenvalue being non-negative is equivalent to non-negative definiteness. Is there any third definition or characteristic of a non-negative definite matrix?
All the principal minors are non-negative.
Which minors?
Principal minors.
Correct. All the principal minors. So, if this is my matrix, then this element has to be non-negative, then determinant of this square, 1 2 first second row and first second column, this has to be non-negative. Then determinant of 1 2 3 1 2 3, determinant of 1 2 3 4 1 2 3 4, all these determinants should be non-negative. This is third equivalent definition of non-negativeness, non-negative definiteness. Now I am saying that every variance covariance matrix, of course I am talking about population variance covariance matrix. In sample anything can happen, so because we are talking about estimates, so every variance covariance matrix should be non-negative definite. Why should it be non-negative definite? Any idea? What happens if it's negative? I mean, if some eigenvalues are negative, what is the problem?
Ma'am, as I told that the diagonal elements must be non-negative. So in that case, if it is negative, then some of the diagonal elements of A must be negative.
No.
Then in that case, the
See.
variance.
Wait. Diagonal elements being non-negative is not a sufficient condition for non-negative definiteness. Means what I am saying is you can have a matrix whose all the diagonal entries are non-negative or even positive, but still the matrix can be the matrix need not be non-negative definite. Means it can still have some negative eigenvalues. So we don't want to allow even that case. So why?
Okay.
Okay, so keep this question in mind. We will go ahead and I hope you will discover the answer to that question during the class itself. Okay, we'll study a few more properties, and while studying those properties, keep this question in your mind, because I'm sure you will discover the answer in one of those properties. Okay, so first let me define what would become expectation of AX when A is some constant matrix of order, say, Q cross P, and X is a random vector of order P cross 1. Okay, so what can I say about expected AX? Ideally we would want it to be something like this, A expected X. Am I right? So let us try to check if that is true. So I want to compute expectation of AX. The orders we have taken them to be compatible. So the overall AX matrix is of order Q cross, it's a vector of order Q cross 1. Okay, A is Q cross P, X is P cross 1. So AX is of order Q cross 1. Okay, so how would I write expectation of AX? Now let me keep expectation aside and we'll try to compute just what AX is. So A let me write as A11, A12 up to A1P, because we want it to have P columns. Then A21, A22, A2P, and AQ1, AQ2 up to AQP. Is it okay? And X I will write as X1, X2 up to XP. So this is the thing whose expectation we have to take. So let us use the properties of matrix multiplication. So so what I have is expectation of, I will have A11 x1 plus A12 x2 plus A1p xp. Correct? This into this. Can you see the arrow also? When I move this, can you see the arrow?
Yes, ma'am.
Okay. Then next row is this second row into this. So A21 x1 plus A22 x2 plus A2p xp, and similarly last row would be AQ1 x1 plus AQ2 x2 plus AQP xp. So each of these is a scalar quantity. Why? Because A11 is scalar, x1 is scalar. So this is an addition of p scalar terms, so it is scalar. So overall I have a vector of length q cross 1 as expected. Okay, we had said anyway Ax would be q cross 1. And now I know that expectation of a vector is nothing but vector of its expectation. Okay, so I can take simply the expectation inside. So this would become expectation of, I can write in a shorthand way, sum over I going from 1 to p a1i xi. Is it okay? Everyone okay with this notation? Then second entry would
Yes,
be
ma'am.
expectation of sum over I going from 1 to p a2i xi and so on. Last entry would be sum over I going from 1 to p a qi xi. Okay so far? And now we said that this summation a1i xi or summation aki xi in general for every k is a scalar quantity and it's a linear kind of thing. So by linearity of expectation, I can take the expectation inside. A1i's, A2i's, AQi's are anyway constant because A is a constant matrix. So they will remain outside the expectation. So what I'll have is sum over I going from 1 to p a1i expected xi. Correct. Then sum over I going from 1 to p a2i expected xi and so on. Sum over I going from 1 to p aqi expected xi. Okay. Now see, this sum over a1i xi we know came from this thing, the A matrix into x1, x2, xp vector. So I could rewrite this vector as, a11, a12 up to a1p, then aq1, aq2, aqp, okay, and here expected x1, expected x2 up to expected xp. Okay, I could rewrite it like this, and this is nothing but what we wanted. So this is A matrix into expected x vector, correct? Because expectation of x vector is nothing but this vector, expected x1, expected x2, expected xp. So what we have proved is expectation of ax is A expected x. Is it okay? Is it okay?
Yes, ma'am.
Okay.
Yes, ma'am.
So I know this looks very simple. You might be having a feeling, why do I need to even prove it? Because you know it's obvious that A will come outside. But we have to be careful. We have to even prove the trivial obvious things. That is the meaning of becoming master of a subject. You are going to get a master's degree. So you should be able to prove even the trivial things. Okay. Even the things which seem obvious you should be able to prove. Because otherwise you can't guarantee. Sometimes even trivial things can actually be incorrect. Things which might seem trivially correct can actually be incorrect. Okay. Now I have a homework for you. So your homework is what happens in the reverse scenario. Means if I have expectation of x, okay, into some scalar, because x is p cross 1. So I can't have a vector here. So x into some scalar a, then can I write it as expected x into a? Okay. Another homework is expectation of A into scalar, because scalar can be multiplied even in the beginning. So can I prove that this is same as A into expected x? And one more homework. Suppose I have expectation of x prime. So x prime would be 1 cross p, and I have some matrix B which is say p cross q. Okay, then that product is compatible. So expectation of x prime B, can I write it as expected x prime into B, or is it further same as expected x whole prime into B? Can you see the difference between this term and this term? Here I am saying expectation of x prime, and here I am saying expectation of x whole prime. Okay. So while proving this part, in between you are also trying to prove this. Expected x prime is same as expected x whole prime. So this is like a sub homework. Okay. So you have to try and prove these things. We will now talk about variance. Okay. Before that, let me take a break of 2 minutes, then we'll talk about variance. Okay, I'm back. So now we'll start with the next property. So we talked about expectation. We will now talk about variance. Okay. So what can be said about by the way, if you remember, I had already given you one homework about expectation of some constant vector into random vector yesterday itself, right? Expectation of mu prime x and expectation of x prime mu, correct? So I am assuming that you could do it, and then we are going to talk about variance. So we have to talk about variance of a prime x, where now a is a vector. So a is also a p cross 1 vector. And then later we will also talk about variance of matrix A into X. Okay. So variance of, you can see my screen, right? Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So expectation of, by definition of variance, this would be expectation of A prime x minus expected A prime x whole thing into A prime x minus expected A prime x whole prime, and then this bracket close. Am I correct? This was our definition of variance yesterday. Variance of any vector x we wrote as expectation of x minus mu into x minus mu whole prime. So if I try to simplify this, this would be expectation of A prime x, and assuming that you did your homework, this becomes A prime mu x. Okay, A prime into expected x, so it is A prime mu x into A prime x minus A prime mu x whole prime. Okay, so this is expectation of A prime x minus A prime mu x into, now if I take the prime inside, it will be A prime x whole prime, and by your formula from linear algebra it would become x prime A, correct? A into B whole prime is B prime into A prime. So x prime into A prime prime, so A prime prime is A, minus mu x prime A. Okay. Now I can try and take A prime common, so this would become A prime into x minus mu x and x prime minus mu prime into A. Okay, so this is expectation of A prime x minus mu x, and this could again be written as x minus mu x whole prime A. Okay so far? Now my claim is, which is again a homework for you. So whatever I use here is homework for you. A prime can be taken outside is my claim because it is anyway constant. X minus mu x whole prime, and then this a can also be taken outside. That is my claim. So your homework is again going from this step to this step. So in general I could write this as expectation of some constant matrix into a vector into another constant matrix, assuming that the products are compatible. So this should be same as A expected x B. Okay, assuming that the products are compatible. So B has to be 1 cross something and A has to be something cross P, correct? Then only the product would be compatible. Okay, this is your homework. And in fact I would say try to extend it to matrix also. So expectation of A M B, where M is a random matrix and A and B are constant matrices, can we write it as A expected M into B. This is another homework. Okay, so you have 2 more homeworks here. Weekend is coming, so you should have more homework, right? Okay, so I am going to assume that it is true and hence it could be written like this. And now this is A. What is this quantity? Expectation of x minus mu x into x minus mu x whole prime would become variance of x, because that is my definition of variance of x, into A. So the notation for variance is generally capital sigma. So A prime sigma xa. We did not introduce the notation yesterday, but yes, you know this is commonly used notation for variance coincidence matrix. So A prime sigma x A. So what we have proved? Variance of A prime x is same as A prime sigma x A. This is what we have proved. Okay. Does this answer my question earlier? Yes, I had asked some question earlier. Does it answer it? Yes, no. No idea.
Yes, ma'am.
Okay, yes, tell me.
Ma'am, that was the non-negative definite that question, right?
Yes, that question.
From this, we can conclude that it is nothing but the variance, right? If the eigenvalues are some eigenvalues are less than equals to 0, then then it maybe this variance may not be greater than equals to 0.
Correct. So if suppose your sigma is not non-negative definite, okay, suppose your sigma matrix is not non-negative definite, then what would happen? It would mean, by definition of non-negative definiteness, there exists some vector A. Instead of x, I am going to use A now. There exists some vector A in Rp, assuming sigma is P cross P, such that A prime sigma A is less than 0. Correct. See, if sigma is not non-negative definite, it would mean that there exists at least one vector A such that A prime sigma A is negative. And if A prime sigma is negative, then that would mean that variance of A prime x for that particular A would also become negative, because we just now proved that variance of A prime x is this. So if this is negative, it would mean variance of A prime x is negative, which cannot happen. Variance of anything cannot be negative. Hence, sigma must be non-negative definite. So we have proved by contradiction. So we assume that sigma is not non-negative definite, then we reach this contradiction, that variance is negative. So we conclude that our original assumption with which we started must be wrong, and hence sigma must be non-negative definite always. Is it okay? Okay. So now next thing that we have is variance of a matrix into a vector. Remember, I am not talking about variance of a matrix, because even though this is a matrix of order say q cross p, because x is a vector, overall ax is still a vector because its order is going to be q cross 1. So I am still talking about variance of a vector. I am not talking about variance of a matrix. Okay. In fact, we won't be talking about variance of a matrix. Okay. Okay. So variance of ax, how would I write? How would I write variance of ax?
Ma'am, we can write it similarly, just like the above one.
Similarly means?
A transpose
Correct.
sigma of A
Oh,
into
no,
A.
no, 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 no. I want derivation. You can't go jump to the answer unless you prove it is correct.
Okay, okay.
We have not proved that it is A transpose
Okay.
sigma A. So I
Okay,
have
okay.
to write. So
Yes,
variance of,
it will be expectation of
correct. Okay.
A x.
Okay, let me try and write what he is saying. So this I could possibly write as expectation of ax minus expected ax into ax minus expected ax prime. Correct?
Yes,
Okay.
ma'am.
So it is, again I am using the same definition. Variance of any vector I can write as expectation of that vector minus its expectation into that vector minus its expectation whole prime. Okay, yesterday we saw this definition of variance. Now again, assuming that you have done your homework, and no, in fact we proved this in the class itself today. Expected ax is a into expected x. So I could write it as ax minus a into expected x. So expected x I will write as mu x, and this would become ax minus a mu x whole prime. So this would become expectation of, let me write one more step, ax minus a mu x, and this is ax whole prime minus a mu x whole prime. So ax whole prime would become x prime a prime minus this would become mu x prime a prime. I assume everyone is following this. If you are not following it, please let me know. Okay. So this would become a times x minus mu x, and I can take x prime minus mu x prime in this bracket, and then a prime could go outside. And now assuming that you proved this, just now I gave you one homework. Expectation of A into a matrix into B is same as A into expectation of a matrix into B. So we need that property here. Okay. So from earlier homework, I can write it as A expected x minus mu x minus mu x whole prime, I could write it again, into A prime. Okay, so as I said, this comes from the homework from the earlier page, so previous homework, no new homework. And then this is A. Now expectation of x minus mu into x minus mu whole prime is variance coincidence matrix of x, so sigma x and then A prime. So what I have proved is variance of AX is A sigma x A prime, whereas earlier what I had proved was variance of A prime x is A prime sigma A, correct? So this was for a vector and this is for a matrix. Okay, so this prime is in the beginning because here it is A prime, so A prime remained as it is, whereas here I have A, so A remained as it is. Okay, so this is variance of a vector when the original random vector is being multiplied by a constant matrix. Okay. By the way, the non-negative definiteness thing we talked about for variance covariance matrix, the same property holds for correlation matrix also. Any guesses why? Why should it hold for correlation matrix? Just now we proved why should it hold for covariance matrix. Why should it hold for correlation matrix?
Because we can write the correlation matrix in the quadratic form of that variance covariance matrix.
Okay, that would become a proof, but I want some intuitive explanation instead of proof. Yes, if you want to write a proof, then yes, this is correct. Good process, good thought process actually. If you want to write a proof, then yes, you can express correlation matrix in terms of covariance matrix, and because covariance matrix is non-negative definite, you could prove that correlation matrix must be non-negative definite. So this is way of proving. Now intuitively, why do you feel it should be non-negative definite? Yes. Okay. Let me go to univariate setup. What is formula? Univariate means of course I have to go to bivariate setup if I am talking about correlations. So what is formula for correlation of xy? It is covariance of xy divided by square root of variance of x into variance of y. Am I right? And now what is correlation of? Are you able to hear me?
Yes, ma'am.
Yes, ma'am.
So what is correlation of these quantities? What is covariance of these quantities? Covariance of x by variance x by square root variance x, and y by square root variance y. If you don't like variance, if you don't like the notation, I could write x by sigma x, y by sigma y. What would be covariance of these two quantities? It would be 1 by sigma x sigma y into covariance of xy. By your properties that you studied in BSc, covariance of ax into by would be ab times covariance xy, change of scale. Okay, and this is nothing but correlation of xy, correct? This is correlation of original xy. So correlation of xy is basically same as covariance of scaled xy, correct? Correlation of x and y is nothing but covariance of scaled x and scaled y. So correlation is also in fact a covariance. Okay, hence correlation matrix is actually one type of variance covariance matrix only, but instead of it being variance covariance matrix of the original variable, it is variance covariance matrix of the scaled versions of the original variables. Is it okay? Hence, whatever properties covariance matrix has for being covariance, those properties would get retained here. Hence, correlation matrix also has to be non-negative definite. Is it making sense? These are some properties of expectation of vector and variance of vector that we studied today. We also discussed some properties of expectation of matrices and you are supposed to solve those as homework. So let me stop here. Do try to work out these homeworks. Thank you.